As we move forward, some things we need to mention the cautions on the central limit theorem. So, some things to keep in mind of when the central limit theorem can be applied and when it cannot be. So, I'll just read this. If the original distribution of data is unknown or something other than normal, the sample size n must be greater than or equal to 30 to be powerful enough to create a normal distribution of the sample means. If n is less than 30, the central limit theorem cannot be applied. Okay, so really important note here. If we don't know what the normal distribution is doing, or what the original distribution is doing, or if we know what it is but it's not a normal distribution in the original data, then our sample size has to be at least 30 in order for all of these ideas to create a normal distribution when we look at the sample means. If it's less than, if the sample size is less than 30, then when you perform all those sample means and you take the mean of sample means and the standard deviation of sample means, then it will not be powerful enough for any of these ideas to work. 30 is not a number that we come to from any sort of mathematics. 30 is just the generally agreed upon value for the sample size amongst statisticians. So everybody agrees, yeah, if you got 30 or more, then that's going to be powerful enough. If it's less than 30, then we just cannot trust the results if you're using these ideas. Okay, so um, on the other hand, and we're just kind of summarize here, if the original distribution is normal to begin with, so let's say you've got normally distributed data and then you take samples and you take samples of size less than 30, then that's going to be fine. That's still going to create a normal distribution of the sample means. If it's originally normal, then you can take any size samples you want and it's still going to be normal. You only have to do something greater than or equal to 30 if the original distribution was not normal or was unknown to begin with. Okay, and we kind of summarized right there. The original distribution is not normal, then your sample size has to be greater than or equal to 30. Your original distribution is normal, then it doesn't matter. It's already normal, so you can take any size you want. In either case, the larger the sample size, the smaller the standard deviation of sample means. So if you take bigger sample sizes, then that means your standard error or your standard deviation of sample means is going to get smaller and smaller. Why is that? Because you always divide it by the square root of n. So if n is bigger, then it's going to make that number smaller. In other words, the normal distribution of sample means will become more tightly packed near the center. Okay, let's see what's going on there. We've got a couple more practice problems here, just kind of round out all the different styles that we want to look at. So let's get to number 2. It says the Nielsen television ratings reported that children between the ages of 2 and 5 watch an average of 25 hours of TV per week. I used to read that and think, oh, wow, that's so sad. All these little kids watching 25 hours of TV a week. And then I kind of thought about it. Wait a second, that's only about, three and a half hours a day. Like that's really not that much. That's perfectly okay. All right. This variable is normally distributed with a standard deviation of 3 hours. And it says if 24 children between the ages of 2 and 5 are randomly selected, find the probability that the mean number of hours they watch TV per week will be greater than 25.5. Okay, a lot of information there. Let's try and organize our thoughts. So as we read through that, we see that, okay, the average is 25. right? Okay, you see what I've got there. So mu is 25. It says the standard deviation is 3. It says if 24 children between these ages are selected, so there's our sample size, 24, n equals 24. And finally, they're asking us to find the probability that the mean number of hours per week from that sample is greater than 25.5. So x bar, the sample mean, is 25.5. Now at this moment, we want to pause and think, wait a second, we just read all of those cautions on the central limit theorem, and it seems like we might have a problem here. The sample size is 24, and that's less than 30. Are we able to apply these ideas? Are we able to use the formula for the z-score for the central limit theorem and proceed? Or can we not do anything with this since our sample size is less than 30? And it turns out it's okay that our sample size is 24. Why is that? Because if we look closely back at this problem, it says this variable is normally distributed. And so since the original data is normally distributed, it's okay if the sample size is under 30. It's normal to begin with, then it's going to be normal no matter what sample size we take. Okay, so no problem. We can proceed here. So we're going to calculate the z-score. So in this case, it's z equals 25.5 minus 25 all over 3 over the square root of 24. If you want to just go for it here in your calculator, just be sure you put parentheses around your numerator and denominator like so. I'll just go ahead and grab my calculator and do that. 25.5, well, now I forgot my parentheses. Parentheses 25.5 minus 25, parentheses divided by 3 over the square root of 24. And that looks pretty good. And okay, there we go. When we round to 2 decimal places, 0.82. Okay. And I'll pick it up on the next page. So there's our z-score. Now, at this point, look back carefully at the problem. And do we want a less than, a greater than? What's going on? They say find the probability such and such will be greater than 25.5. Okay. So we're going to go with probability that capital Z is bigger than our z-score, 0.82. And from here, if you remember how to handle a greater than, we'd use a complement. So we're going to figure out 1 minus the probability that Z is less than 0.82. And we'll go with our table. So I'll give you guys a few seconds. Go to your table and look up the z-score of 0.82. And we'll continue on. Okay, I'm going to move ahead. Z-score for 0.82 is 0.7939. And we do a complement there. 1 minus that gives us our answer, 0.2061. So if you were to pick 24 children between the ages of 2 and 5 and find the average number of hours that they watch TV per week, the chances of it being greater than 25 and a half would be 0.2061. Think, wow, you know, that's a pretty small, I mean, just think about this. And it's like, I know I'm kind of reflecting on this a lot, but right, the average kid between those ages watches 25 hours. We're saying do a sample. What's the chances that the sample is bigger than 25 and a half? That's only half an hour bigger. But even moving it by half an hour, because we're doing this for a sample size, the chances are maybe lower than what you would think, only about 20%. Because you're looking at 24 kids, and some watch a little more, but some watch a little bit less, and the average actually comes out, most likely that average is going to be very close to 25. So even going up this high, the chances are smaller than you might think. Okay, let's go straight into number 3. The average amount of meat that a person in the US consumes per year is 218.4 pounds. Okay, so as I read that, I recognize there may be some in the class who are vegetarians or vegans. Most classes I teach, there'll be 1 or 2 or 3 vegetarians or vegans. And so this problem may be a little bit offensive to you. If you are that person, if you're a non-meat eater, I got a lot of sympathy for you. Actually, when I was in college in my early to mid 20s, I was a vegetarian for over 4 years, and it was a really really good experience for me. And there's a reason that I stopped doing that, but I won't get into those details. But hey, I fully sympathize with you, and I actually think a lot of us would be better off eating a little bit less meat than what we do. Okay, so that's not to go too far down that line of thinking, but all right. Um, Let me read this again. The average amount of meat that a person in the U.S. consumes per year is 218.4 pounds. Okay. The standard deviation is 25 pounds, and the distribution is normal. Okay, again, we've got a normal distribution for how much meat people eat. That makes sense, right? A lot of people are going to eat about the same number of pounds per year, and then it gets further and further, less and less people the further away from that you get in either direction. Okay, let's go ahead and note we've got our mean, we've got our standard deviation. No problem. Get to part A. If a sample of 30 individuals is selected, find the probability that the mean of that sample will be less than 210 pounds per year. All right, so pretty straightforward here. We're taking a sample of 30, so n equals 30, and x bar is 210. The probability that the mean of the sample is less than 210. All right, so we'll go ahead and find the z-score, and you see I've already got it right there. So we've got z equals 210 minus 218.4 divided by 25 over the square root of 30. Use parentheses in your calculator, and you should get negative 1.84. I'm just going to do that here again in my calculator quickly. Make sure I get that result as well. Yeah, negative 1.84 when you round. Okay, perfect. This is a probability less than, so we're just going to go for it in the normal traditional way. The probability, or the most straightforward way possible, z is less than negative 1.84. And you see I've already got the final answer there. If you look that up in your table, negative 1.84, maybe for yourself, confirm that it is in fact 0.0329. And yeah. Okay, well, again, it's like, wow, that probability is so low, just over a 3% chance, right? We take 30 people. What's the chances that the average amount of meat they get per year is at 210 or less? Like, that's not that far below, but still, that probability very small. Okay, we're gonna highlight this fact even more in part B. Let's check this out. In part B, we're gonna keep everything the same except increase the sample size. In part B, it says, if a sample of 40 individuals is selected, find the probability that the mean will be less than 210 pounds per year. So all we're doing is changing the sample size to be 40. All right, I'll just kind of bring this back right where in part A it was 30. Now this would be a lot more interesting if we were in class together. At this point, I like to ask everyone, hey, if we change the sample size from 30 to 40, everything else is the same. What's that going to do to the probability? Is it going to make the answer to this probability bigger than this probability? Or will it make the probability smaller? than this probability? Would it stay the same? What happens if we make the sample size bigger? Now, if you're in class together, people would respond to that, and we could be like, okay, well, interesting. Let's see. Let's just go ahead and do the calculations, and we'll find out for ourselves. So finding the z-score here, now it's 210 minus 218.4. Well, that's the same. What we're dividing by, though, is 25 over the square root of 40. So again, of course, all that changed was 30 became 40. Notice what that does to the z-score. When you compute this, your z is negative 2.13, where earlier the z-score was negative 1.84. So our z-score went further in the negative direction. What is that going to do to our probability? Well, again, let's find out. So if we look up the probability for z less than negative 2.13, look up negative 2.13 on the table, and you get 0.0166. A little bit over 1%, where this was a little bit over 3%. Actually, it looks like, well, the probability got smaller, and in fact, it just about got cut in half. Right? This number is about half as big as that number. So what happened? Well, when you increase the sample size, then what you've done is you've made it even more difficult to get further away from that mean. The likelihood is even less to get further away from 218.4 when you've got a larger sample size. Well, why? Because a bigger sample size means that more of the values are going to balance each other out, and the sample, or sorry, the average from that sample of 40 is going to be closer to this. So if we're still taking it to be 210, then that likelihood drops quite a bit. Here's kind of another drawing similar to the one we did a couple videos back, the first practice problem that we did. So as you increase the sample size, right? So here it's like, you know, your just regular normal distribution, regular old bell curve. If we make the sample size to be 30, like here, it's like we've pushed the data toward the middle. So it gets stacked up and it gets narrower as you go further to the outside. As we increase the sample size even more, guess what? It pushes together even more, and it gets more and more unlikely to get further. And that's kind of like an awkward drawing there, but it gets even less likely to get further to the outside the more it's stacked up in the middle. And that's where we get the name central limit theorem. It's all pushing toward the middle. Okay, you notice there is a part C to practice number 3. Let's take a look at that. I'll go ahead and read it. Find the probability that one person selected at random consumes less than 210 pounds per year. Okay, we're still keeping that 210, but now we're saying don't take a sample here, just look at one individual. So what's that all about? Okay, well, if you're only selecting one person and it's not a sample, then we're going to think of it in the way that we did back in chapter 6 when we first learned the normal distribution, because that's how the problems worked there. We pick one random person and think, what's the chances that they consume less than 210 pounds per year? And again, if we were in class, I would ask, you guys, do you think the probability will go up or down compared to parts A and B? Well, let's see what happens. So here, when there's not a sample, it's just one individual, then we don't think of it as X bar, right? The 210 is just a data value X. And when we plug in to the original Z formula, It's 210 minus 218.4, simply divided by 25. And in that case, you would get a z-score of negative 0.34. If you look that up, negative 0.34, you can tell that z-score is getting closer to 0. So looking it up in the table, negative 0.34 would give you 0.3669. And yeah, compared to the other probabilities for parts A and B, that is so much greater. Right, almost 37% of the population eats less than 210 pounds of meat per year, where in parts A and B we were looking at samples of size 30 and 40, and the chances of those averages coming out to be less than 210, very small, but as opposed to one individual. Okay, we have to point something out here. This is so incredible. I cannot resist. And it's really interesting too. For part C, it's probably best to think of it the way we just did. If you're doing one person, you don't think of that as a sample. But could we think of it as a sample and still use the Z formula for the central limit theorem? Yes. Or think of the sample as being size 1. Why not? Like, it could be a sample, just the sample size happens to be 1. Like, well, that's kind of weird, but okay, I guess we could think of it as a sample of size 1, randomly pick one person. So what does that mean? Then we'll think of X bar as being 210. So, hey, if it's only one person, well, then what's the average for that one person? Well, it's just whatever that data value is, right? So like the average of the one number, 210, is still 210. So we could think of the average for that sample, the sample mean, as being 210, and n equals 1. We'll plug that into our formula. And guess what? It's not going to change the z-score, because what would happen? It'd be 210 minus 218.4 divided by 25 over the square root. But here n is 1. And well, what's the square root of 1? Right there, it's just 1. So 25 over 1 is still just your 25, right? And you end up with the same z-score, which is going to, of course, lead you to the same probability. I didn't write all that part out, but we would end up with the same probability there for sample size 1. Okay, wow, this is so cool. It turns out, even back in chapter 6, we were doing the central limit theorem, but we were just always thinking of it as a sample size of 1. Isn't that crazy? Math is just so cool like that. That we start with simpler, and when we go to the more complex, it turns out the more complex reveals what was really going on back in the simpler. This was just a special case where the sample size was 1. So amazing. All right, we got to stop this video here. More practice problems next.